these contestants don't know anything of the field, and they don't know anything of the presentation as far as you don't. So when I open the file here, then they see first time the topic, and then they start improvising in this topic. So let's see what happens. But the rule is that I open the file, or there might be some hassling with everything. Oh, the mouse is there. No. Yeah, it's here. I open the file, then comes the talk, and then it's supposed to be a scientific talk, and you are kind of the audience who says how fluent is this person and how nice is the talk, and if there's some humor, that's fantastic, and so on. And then he concludes it, and you get applause, and then comes one question. It should come from the person who made the slideshow. And after that question, we measure the acoustical response of you by a standard sound pressure level meter, and that gives the value or the Q value or the measured quality of this talk. So, and the winner gets a bit more wine than the others. And
I want some wine now.
We have, or yeah, why not? Yeah, the length of the talk is ideally about 5 minutes, but that's we are not too fuzzy about that. So the first guy is Dr. Susi Toma from Department of Applied Physics and School of Science. And you like to have it in this? Yeah.
I can be here, actually.
Okay. Okay. So now I open the file of Susi Toma, and I open this and press here.
Ladies and gentlemen, dear colleagues, it is a great pleasure to present this talk on nonlinear time-frequency processing applied to binaural aided hearing to such a distinguished audience. As you know, our lab is one of the world's forefront experts on this topic, and I have spent most of my professional life working on this, so I hope I won't get into too much technical specifics for you. And my name is actually Toma Susi and not Susi Toma, but since these are pretty uncommon names, I forgive the organizers for these small lapse.
Thank you.
So let's get right to it. So as you know, noise and other kind of reverberations and disturbances can reduce the understanding of speech with hearing impaired people. And there are several types of microphone arrays that are designed to increase the signal-to-noise ratio and basically get a better recording of the audio. And in our work, we've been using spatial filtering using a combination of BTE signals. And this requires a relatively high data rate at a limited frequency range. And the processing called DIR-AC is applied to binaurally fitted BTEs. And this gives you spatial filtering for direct sound. And also we can attenuate the ambient and reverberant sound and give you the better signal quality. And the good part is that the relatively low data rate is required between the BTE devices. And you can see here a schematic of the device in a kind of a model ear with some specifications of the distances, but I won't have time to go into that. About the actual processing, so we measure the active intensity vector, and that defines the diffusiveness of the sound. And there we have the microphone channels in, and there first we do some time frequency analysis, either short-time Fourier or filter bank analysis. And then to estimate the direction and diffusiveness, we use a so-called energetic analysis. And from this input data, we measure the azimuth angle, the elevation, and the diffusiveness. And using this data and the algorithms we've developed, we reproduce point-like virtual sources that reproduce the diffusiveness, and then we get the output signal from the device. And the point of this is to do directional analysis of the audio signal. And at low frequencies, without the so-called head shadowing effect, which is a commonly known thing in our field, we can get the real pressure gradients. And at high frequencies, we do take into account the head shadowing effect, and from this we get the active sound intensity for the so-called y-axis. And the DOA and the diffusiveness are estimated from the vectors of these intensities in the x direction and the active sound intensity for the y-axis, for the low and for the high frequencies as defined here. And what's the use? So what do we gain from this? So to kind of quantify the fidelity of our audio signal, there is a so-called speech reception threshold that we measure at different signal and noise azimuth directions. And in this plot here, you can see the results for the DIR-AC spatial filtering and normal diotic listening. And looking at the plot here, which is the signal-to-noise ratio for different signal-to-noise levels, we can clearly see that the square boxes for the DIR-AC, we actually get much better signal-to-noise ratio. And it's almost 10 decibels here, the difference to the normal diotic listening. So this is quite a significant boost in the audio quality. So to summarize quickly, we have been developing the DIR-AC processing applied to bilateral aided hearing and analyzing the signals in the time and frequency channels using 2 microphones for each device. And with these two microphones, we achieve effective broadband spatial filtering. And all of this we achieve with a low bit rate for the data transmission, so we don't need to use any high throughput data transmission channels. And applying this for a real listening test with the speech reception threshold, for various speech and noise configurations, we really achieve a huge improvement in the SRT with this DIR-AC processing. And with that, I'd like to thank you all for your attention, and I'm open to any questions. Thank you.
Thank you, Thomas. And I have one question about, can you show me again those results? Yeah, here you see in the signal 0 and noise 90 case and noise the second case, but in the last case it's 27 decibels the difference. Can you imagine why?
Well, in this case the level of noise is actually 0, N0 case. and for this case, the algorithm really shows that it's not only about the noise processing, but we really can just from even clean signals, we can get a much better signal-to-noise ratio. And this is very useful for example, if you have the hearing aid and you have a quiet, normal room and the person next to you is talking to you. There's not much noise, but you can really, really capture the whispers with this method, so it's quite useful.
Okay. Thank you, that was good. And now wait a minute. We thank again Thomas. moment. And we move to the second talker in this. And it is Mr. Olli Santala. And here comes his show.
Okay, good afternoon, ladies and gentlemen. Thank you, Chairman, for these kind words. Dear colleagues, it is my pleasure to introduce to you my talk on passivation of black silicon surfaces with active LED displays with such chemical methods. But I would actually like to say, before we go into any details, that black silicon is groundbreaking, and the universe has great benefits from this. But before going to that, let's have a look at the background. And we have various methods to fabricate this BSI method. As you can see in the figure in the center of the screen, can you see my, yes, okay, here. We are applying 200 nanometers in this figure, so this is a really small scale experiment. And the problem with this small scale experiment is that the large surface area leads to increased recombination velocity. And recombination velocity in this case is shown clearly on the right side of the image, showing this peak over here. That is the biggest problem we have. But nevertheless, efficient surface passivation is needed. So how do we do that? Well, experimental data and process details show again that when we're going to 10 micrometers in this figure, that we can obtain quite interesting looking nature surfaces. And black silicon etching is done in order to obtain these figures. And maskless cryogenic DREA is done in order to have a standard plasma etching process here. And as I mentioned earlier, this black silicon is a groundbreaking thing. And now you can see that when we apply surface passivation into that, we can have thermal active LED displays at 200 Celsius. And that is something that isn't normally seen in laboratory experiments, because 200 Celsius is so much that you cannot have it just by going into a sauna. But what we wanted to do is to increase it even to 430 Celsius because of the post-deposition angle at that degree. And what we obtained was that when we had this 10 micrometer thing-a-ling on the left side, we can increase the thickness to 20 nanometers. And what we want to see from that are the results. Recession sample RS is the lifetime of these two parameters that are very well known in the industry nowadays. We have on the left side wavelength of a couple of nanometers. This is actually fire. And on the right side, the fire has changed slightly because, as we can see from this curve, when you apply heat over 225 Celsius, we get this red curve, which moves the intensity of the fire to a little bit to the left from the processing plant. And that is obtained by high resistivity mono SI. Okay, before I go to conclusions, I would like to say that this fire that we got wasn't an easy task to do because we had minority carrier densities, and we had to do really small-scale experiments to find out this. And actually, a box this big was on our table, and we put some wires into it and did this again, this high resistivity mono SI, and what we saw that after 2 weeks of processing with MATLAB, we found out that the concluding remarks that I'm going to present to you are the lifetimes in the millisecond range and rectangle values below 1% can be reached. And that is the groundbreaking thing about the black silicons that I mentioned. Lifetime in the millisecond areas. Think about that. I don't think that has been achieved before in the industry or in the research field. But even though there are still some problems, because black silicon surfaces can be passivated with this active LED display. And that results in the negative charge at the interface. So we still have some issues, and we have these black boxes which represent the unknown areas. So there are quite a few, 6 times 10 black boxes. So I hope to have a lot of funding in the future, and I hope you liked my presentation. This concludes it. Thank you.
Thank you, Mr. Santala.
Any questions?
Yeah. There's one.
Okay, thank you for the excellent presentation. So, what would you say, what is the benefit, or how much do you benefit from the black silicon as compared to the standard silicon?
Well, as I mentioned earlier in this slide, the benefit is that we can increase the Celsius degrees from 200 to 430. So that's quite a lot. That's twice the benefit. So,
yeah, thank you. We don't have time for more questions, so let's thank again Mr. Santala. Quietness. And then we move on in the session. This comes to Heikki Harju. Let's see. Do you want to have this?
No, I can.
Okay. So this is maybe the most demanding, I would say.
Well, hello everybody. My name is Heikki Harju, and as a chemist I am the absolute authority in the world in the area of P2P VOD and the steady state and scalability of this technique. So thank you all for coming here to listen to me, and the chair for presenting me and giving me this time to present my excellent results. So, first of all, the model for the P2P VOD systems. Well, the lifespan of a peer consists of overlapping phases. There's a transfer phase, which is marked as X, the sharing phase, marked as Y, and then there's the playback phase. And the playback phase is a function of both the transfer and sharing phases, and it's a function of time. And then for the model for this P2P VOD, we built this deterministic fluid model, which describes the system dynamics when sharing a single video file. And the model takes explicitly into account the playback phase, which is, of course, the most important if you're watching a video. So then let's look at the fluid model a little bit more, without impatience, please. Because everybody knows if you try to stream some video somewhere from the... it really sucks if it starts sticking. And so let's try to be patient here first. So first, let's switch it to a nonlinear system. When I first see... can you see the red dot? Yeah. So first we can see the x as a function of time, and the y as a function of time. Looks like that. And then in the end we get theta, which is a minimum of function which takes into account both the x and the y, as well as some other variables. So then here is the complete thing. You can see how the lambda, first with the lambda we can calculate the x, which then of course leads to a y, but of course we have to subtract the 1 minus xi from it. And then of course the whole thing is the theta as a function of x and y, and gives us the z, which in this case presents the patience of the person who is trying to watch the thing. Yes, and of course, always when you're doing this calculation for VOD, you have to remember to take the eta, the value that's calculated in there, in the theta function. It always has to be less than 1. Because 1 represents the sort of patient person like Buddha, who doesn't get angry at anything. And of course, everybody's a little bit impatient, so the eta is always less than 1. So then let's compare the fluid model to stochastic and BitTorrent simulations. So first of all, we can see here, figure 5, the comparison of fluid model. These are the solid lines against the stochastic model, which is the dashed line, with the patience factor being half, and then this loss factor here. Remember the line that goes out of the function, the box. That being 0.8. So as you can see, there's a clear difference between, of course, this is the sort of theoretical line, this solid line over here. Then you can see there's a definite difference in how these lines work. When you have the stochastic model, which is basically builds up into this theoretical line and then sticks there. But then you have these fluid models, which then go in a more interesting fashion. And then figure 4 shows the comparison of the fluid model. These are, once again, the solid lines against the stochastic model, once again, the dashed lines, and the BitTorrent simulation, which is the solid jagged line, this red here, going like that. You can see this, of course, the other ones are calculation. This is actual real-time data. And then here are the values. So this is the upper panel is the loss factor is 0.9, and in this one the loss factor is 0.3. And once again we can compare how these different models compare with the actual reality. And of course here we can see here's the jagged line. It follows pretty well actually the stochastic model, and not so much the fluid model. The fluid model seems to be in this case as you can see, but then we have the red lines, and in that case actually in that case as well. The stochastic model seems to be the more accurate one in describing this phenomena. So then the steady-state synthesis based on the fluid model and the stochastic simulations. And here we can once again see the patience factor, and here's the loss factor. And here's DL. We all know what that means. Of course, it's deadline. And well, it's not such a problem if both of these, especially if this is nearing 1, but in the smaller ones, and this white area presents the sort of area where it just doesn't work because because people are too impatient and there's too much of the stuff is lost, so it doesn't work in that area. So these red areas are where we want to be, and of course this ultimate limit here, this UL, that is the best one. Okay, and then in this other one, then we have this the same sort of figure, but in this case we just have we put the x and the y in the same figure. So then conclusions. Basically, this calculation system is it's scalable for any patience factor. It's very stable, the calculations. Consequently, the system is also stable for any with this lambda factor, which was affecting the x in those calculations. For any of that, the performance, the playback quality problems. As said, there's problems if the patience factor is too low. So then people will just get angry and throw the computer away or something. And then the performance scalability. And basically, it's scalable to even larger files, but only if the patience factor is large enough. So if people are patient enough, then you can also stream these larger files and not just the very, very small clips like GIFs or something. As necessary conditions, this mu has to be larger than 1 over z. Okay, any questions?
So yeah, I sense some activity here.
Thank you very much for this very new angle for the topic. I just was wondering what's the role of Z here. It was given in the figure, I think, in the last.
Well, as we can see, Z comes from here. It's the boundaries in which we work, which contains both the X and the Y. And of course, out of it comes the Y comes out of the system, and then you also have this loss here that goes out of the Z box.
Okay, thank you. Okay, and then the last. Talk is by Alex Popa. There you go.
Run away. Hello everyone, thank you very much for being here. It's really a pleasure to see so many people at a talk which is random. Actually, I'm very surprised because usually at my talks which are announced and prepared and so on, I see 5 people maybe, and here at such a random talk I see so many. So perhaps it's a good idea at my next conference is to make random talks. Also, I'm very happy I don't see not too many of my colleagues here, and I'm even more happy that I don't see my students here. So today I'm going to talk about construction of a 3D environment map from a laser range measurement data. Yeah, okay, so thanks for the help from the audience. Well, I have a good topic today. Lasers, everyone likes them, so that's cool, But I don't understand what's with this soda can from the slides. We'll get to that later. I hope I'm not offending someone else's research too much. So the first step in our research is to model the object geometry from range image data. So basically, we have an iPhone, we want to make a photo and to, model somehow the image using lasers. So you see, you have some trees. Well, what else can you have here? I mean, it's Finland. It's you could have chosen some, I don't know, women or I don't know, something more interesting. You've chosen trees, not even an animal. So, you see some trees, green and so on, and black and white. And in the fourth image is our real image, which was captured. So let's go to the next step. Now, what we're trying to do here, to register local maps. Well, I mean, on the good side, you can see I have a lot of pictures on my slide. The bad thing, I have very few words and I don't know what to say. So I guess the images are self-explanatory, so you can understand from this. Now, it's even worse. Now we have formulas. Okay, so the third step of our research is to reference all submap data to a common global frame. So basically, we want to gather all the objects we have seen so far into, in a common picture and to make connections between them. So we have a big formula here, which has some Latin letters in it. I apologize, there is a mistake in the formula, so I'll not really go into details of that one, so you can see here some objects which are moving, some, rectangles, dashed rectangles, dots. Okay, so now we're having an example. Again, forest. Come on, I was expecting more variation from it. So we have an example of our research. Here is a picture with some trees. It's what shall I say about it? I mean, And now we have the result of our research. Hopefully, something interesting. So here you see the 3D representation of the forest. I mean, which is basically like the original one. It's flat thing with some things going up and down. And we have an object there which, has 3 coordinates and is moving around the forest as well. Perhaps this is recording the data, I don't know. It might be. So the conclusions, yay, I managed to get out of it. A method for 3D localization of mapping of large-scale outdoor environments was presented. So the machine you see here was moving around the forest and representing all the things. Finally, I got out the idea. And, the method consists of 3 main phases. Well, first we have to extract the geometric feature models from the range measurement data, and then we have to compute relative alignment between the sensor point of view and the different point locations, and then we have to transform this submap data into a common frame of reference. So if you get somehow the idea, first we just play with the robot in the forest and measure everything, and then we go to the lab and write something about it, and finally we make some pictures and make such a great presentation to the audience. So that's my research about. Now can I go? Thanks.
No. There will be one question, I hope.
I want to know who has made this to me. Okay. Thanks.
There you go.
Okay, thank you. I have one question. Can you tell what's the main challenge related to the method?
Well, I can guess the main challenge. I can't tell for sure, but, I guess, if you are moving the robot in the forest and, one challenge is there might be wolves and other things, And, depends when you have done the measurements. If it's VAPU, then are even more challenges around. But now, half seriously, I think the challenge is to overlap these images and to create a sort of, global image of the forest. Because, if you have a photo, then you can understand the objects around. But if you have more photos, you have to gather them somehow into a sort of common shape. That's what I would suspect. But still, I think the main challenge is the one with animals.
Okay, thank you.
Yeah, thank you too.
Okay. So we are really close to ending now, and just first of all, I have been the chair, but I would like to thank everybody in the committee. Samuli Aalto, please stand up. Pekka Forsman. And Mervik Paulastokrökkel is not here, and Hele Savin. And Simeon Delikarismanias, and our secretary was Miss Anne Hirvonen, who was in the reception, I think, and public relations came from Anni Aarinen.
And then, of course, we want to thank Ville for doing most of the stuff.
And next thing is to give out or publicize the winner of the Best Poster award. And I have the results here. I just got from them. And somebody won who got 11 votes, which is quite many. Yeah, most of you got votes. But the winner is a poster with name Eurocode-based design of hard rock reinforcement by Lauri Uotinen. Lauri, are you here? We should have some music here.
Something dramatic, maybe.
Yeah. Da-da-da-da-da. Thank you for coming and making good presentation.
If there was someone who was interested about copying the poster, since it wins awards like this, the web page address to obtain the PowerPoint is attached to the poster on a post-it note. Okay. So please copy.
Okay. Yeah, thanks. And then I have the results for this ISTAT talk competition, if I haven't lost them. No. First, we do it in a way that I ask all of the talkers here, and we give the nice awards, one by one. Yeah. Here is Toma. Thank you. Olli. Thank you. Heikki. Thank you. Alex.
Thank you.
Thank you. And the winner of the contest was by 0.3 decibel difference was Mr. Olli Santala. You get 2 awards. Thank you. And these guys were really brave. Please give them a big hand. And that's pretty much it. And this concludes the day, I think. And yeah, there's some free booze and something to eat still. Please stay with us for some time.
Thank you.
Bye-bye.